Hi there. This is a demonstration of our project, Prediction Survival on the Titanic using machine learning. Titanic dataset is one of the most famous beginner dataset in cargo, and it will be a great way to showcase the full ML pipeline. During this demo, I will introduce four models or algorithms that I used in this project. The goal of this project is to use labeled data to predict whether a given people can be survived or not on Titanic. This is a typical supervised classification problem. I was not just building the models, but also compare them, study overfitting with learning curves, and explain what features mattered most. And the project is hosted in Kaggle. Here is the link. I used the Titanic dataset in cargo. The dataset contains passengers' details, such as class, sex, age, fare, and whether they survived or not. The task is to predict survival by a given passenger who is not in the dataset. I created new features, for example, the title from names, family size, is alone, and deck from cabin info. Family size is calculated based on the number of siblings and the spouse. These new features will add meaningful patterns beyond the raw columns, as I think they may be related to the possibility of survival. I also trimmed some features like a passenger ID and a name as they look irrelevant to the survivor. Finally, I got these features. I'm using Python scikit-learn for modeling and matplotlib for the figures. Data preprocessing include handling missing values, scaling numbers, and one-hot encoding categorical variables. Those are all wrapped in a scikit-learn pipeline. One-hot encoding is a way to turn categorical data like a color, red, blue, green into a numerical format that machine learning models can understand. In this dataset, the column sex, title, and deck have to be encoded by one-hot encoding. In this slide, you will see colors encoding and gender encoding. For example, the red color can be encoded as 100, blue encoded as 001. Another example is the gender. The male encoded as 10 and the female encoded as 01. I trained four models, also known as algorithms. Those are Logistic Regression, K-Lear's label, or KNN, decision tree, and Gaussian Naïve Bayes. This mix gave me both linear and nonlinear approaches. Let's dive into more details for these models. Logistic regression is a linear model that predicts survival probability using weighted sum of features. Think of this as a straightforward, easy-to-read map of the group. It works by taking all the passenger details like their age, class, or fare, and giving each of the weights or an importance score. It adds all those scores up to calculate the probability of survival. The best part is it's simple, super fast, and because you can see these importance scores, it's really easy to understand why it made the certain prediction. K-Lear's label or KNN is a non-parametric model that classifies a passenger based on the majority class and its closest labels. Easy to understand but sensitive to dataset size and noise. This model is all about peer pressure. Instead of building a complex rulebook, it's simply looking around. For a new passenger, it finds the, say, 5 most similar passengers in the dataset, their closest labels. If the majority of those labels survived, it predicts survival. It's a very intuitive idea, but it has downside. Its performance depends on having a clean, well-organized data set, and it can be slow with a lot of data. The distance between P1 and P2 are measured by the Euclidean distance by using this equation. In this diagram, the new data set is closer to the red category because in a certain distance, there are 3 red points but only 2 green points. Decision tree is a tree-structured model that splits data into branches based on the feature values. This one is exactly what it sounds like. It makes a decision like a flowchart. It asks a series of yes or no questions to sort passengers. For example, is the passenger female? If yes, were they in the first class? By following the branch's path of questions, it arrives at a prediction. This makes it very powerful and easy to virtualize. It can love the training data a little too much, memorizing every detail until it can't make a good prediction on new data anymore. But there is a problem, we call it overfitting. Gaussian Naïve Bayes is a probabilistic model based on Bayes' theorem. Assuming features follow the Gaussian distribution and are independent, it's fast to work well with small data. But the independency assumption is often too strong. This is the speed star of the group. Based on probability theory, it calculates how likely a passenger is to survive based on the probabilities of their features. It's called naive because it makes a big assumption. That's all these features like age or ticket class are completely independent of each other. We know this is not always true in real life, but this assumption allows the model to be blazingly fast and surprisingly effective, especially when you don't have a huge amount of data to work with. I split the dataset into training and test set. The ratio is 80 to 20. And use the five-fold cross-validation for more reliable evaluation. It means that I split the data into 5 equal groups or folds. Then I train and test the model 5 separate times. Each time I use different fold as the test set and the other 4 combined as a training set. In the end, we just average the result from all 5 tests to get a final, reliable score. The result shows that logistic regression performed the best with accuracy around 0.84 and KNN performed the second. Decision tree tended to overfit, and the Naïve Bayes was less accurate. The confusion matrix figures in Jupyter Notebook tells that what kind of errors this classification model is making. The learning curves confirmed this. Decision tree had a high variance, while logistic regression shows a perfect curve. Logistic regression accuracy is around 85%, and the validation is close at about 82%. The small gap shows a stable generalization and converged at about 400 iterations. Here is the KNN with the k equals to 11. Training accuracy is slightly higher than validation, but the gap shrinks as we add more data. This means KNN benefits from a large data set, though it's a bit less stable than logistic regression. The decision tree reaches almost 100% accuracy on training, but validation is much lower, around 75 to 80%. It's a clear sign of overfitting. This model memorizes training data and doesn't generalize well. Naïve Bayes starts with a lower validation accuracy around 67%, but improves as data grows. Reaching close to 79% is a simpler model, limited by assumption, but it can't match logistic regression, but still shows steady improvements. I didn't just want to know if someone survived. I wanted to know why. So I looked at what the model considered the most important. The findings were very clear. Gender and class were everything. If you were female or in the first class, your chances increased. if you are a male in the third class, your chances reduced. As a fun check, I tested the model with Jack and Rose from the Titanic movie. The model predicted Jack would die with very high probability 0.9 and Rose could survive with probability 0.94, matching the movie ending. In conclusion, this project demonstrated the full ML workflow, including data cleaning, feature engineering, model training, evaluation, learning curves, and interpretability. The Jupyter Notebook also have code to find the best k-value for KNN. Future extension could include ensemble model like a random forest or XGBoost. Thank you for watching. If you are interested in my channel, please thumb up and subscribe for further updates.